This conference will now be recorded.
Good evening, sir.
Good evening. Very good evening, Deepa. Am I audible to you?
Yes, sir.
Okay. So, Deepa, today we'll be learning a very interesting topic, that is optical fiber, which has great applications in our day-to-day life. Madam, can you ensure whether it is recording or not? I think it is recording. Okay. So if anything is there, you tell me in message.
Yes, recording,
okay?
recording,
So,
recording.
okay. Okay, fine. So optical fiber, it has lot of applications in our life, in modern life, at least I can say. You might be thinking, sir, why this optical fiber you are taking as a topic today? Because the optical fiber is a device which is, first of all, has lot of technical applications, technological applications. On top of that, the principle of this optical fiber we have already learned, that is total internal reflection. So we'll see how the simple phenomenon of light, or simple phenomenon of refraction or total internal reflection, can be used in our day-to-day life as a technological revolution. Okay, so and then we'll take a few numerical examples on total internal, like how just from the concept of total internal reflection we can solve those problems. In general, those problems are being asked in board exam as well as various competitive exams. Okay, so let us first learn what is optical fiber. An optical fiber is thin, as good as hair. Hair is very very thin, right? Some micrometer thick. Okay, so an optical fiber is a thin long strand made of quartz or high quality of a glass coating, relatively lower refractive index, and it used and it used guided as a guided medium for transfer place to another. Optical signal. So optical signal. In fact, nowadays not only optical signals are also being transmitted. Telecommunication optical fibers are being used. I'll just show you few applications over here. See this kind of fountains of light you might have observed, you might have seen in the market. Okay, so for decoration. So you know what you have here. You have a bottom, you have a bulb of light, and see this thing kind of plastic wire. So like most likely thin plastic, more you'll see thin plastic wire. Okay, they are, see there, one end is actually attached near the bulb at the bottom, and the other end is actually nicely arranged, and they are free. So what happens? The light, see optical, as I said, these optical fibers are used to transmit light. Transmit light means light will be going through them without any attenuation. Okay, without any attenuation, in the sense without any loss. Whatever light is entering fiber, that up to the, so what you will see at the top of each, see the free end, each free end will be glowing like bright. Okay, so it will like look like optical fountain. If you search in internet, you might get many other colorful optical fountain. Okay, so these are actually made up of, each of them are and optical fiber. Okay, so you look now, these in wires. You use wires in your home. If you have telecommunication in your home on, okay, see the etc. See, these kinds of wire outer simple covering, and see each of them are optical fibers. These are all actually layers in that. Okay, we'll just try to see. There are many, and actually, okay, voice is not audible. Okay, so how now is my voice is audible? My internet is all right. Even can you check hearing now? Can you write whether you're able to hear now? This is really problematic. Okay. So how about now, madam? Is it audible? Somewhat better?
Yeah, it's better.
Is it some
Better,
okay?
better.
Okay, so shall I continue? I don't know up to how, like, up to what you people have heard. I'll just repeat a little bit. So see, optical fibers actually have many layers. As I said, it is made up of high quality glass or quartz, high quality glass or quartz, and it is coated by glass. See, the inner core, inside the inner core, you can see this kind of, so these many layers are there in the optical fiber. First you have the inner core, which is called simply core, and just top of that there is a coating. Okay, that is another material. So if this is quartz, suppose this is quartz, okay, if it has refractive index n1, so this is called cladding, as you can see. So optical fiber has many layers. So cladding, it is made of some glass. This is made of glass cladding, and suppose refractive index is n2. N2 is actually lesser than n1. That means the core material of the optical fiber is having greater refractive index, and this is the coating, buffer coating. It is called buffer coating. This is also somewhat made of glass or maybe of different refractive index, obviously, and there will be a material to give some strength to this fiber, and outer covering, as I have shown you. See, this is the outer covering, So this is the outer covering. Then you have, this is the buffer, the covering of the fiber itself, as you can see here. And strength provider, okay. And finally you have the outer covering, okay. So I would have given these two figures together, okay. So it would have been better again. Anyway, so this is to just show you that there are many parts of this optical fiber, many parts. In fact, we'll be discussing what is the principle, how light is transmitted. You know, the what is the beauty of optical fiber, what is the advantage, of using optical fiber rather than other like, see, electric signal nowadays electrical signal also is being transmitted through optical fiber. Why don't we prefer conductor? Conductor, you know, there will be huge loss. Even many other things are there, okay. So basically there are other fibers, so why don't we use those things? Because there will be penetration depth, the attenuation of the signal happens. If you see, if you have some signal here, see some intensity I, you will see at the end of the, see, suppose you are just sending the signal for 10 kilometers. So see, earlier days, I don't know you whether you people have come across this thing. See, if you have a cable, TV cable, they goes kilometers after kilometers, and see the people who are at 10 kilometers, they see very good pictures, okay. But people who are at 50 kilometers away from the source, 50 kilometers away, their pictures will be very bad. So this happens because of the attenuation of the signal. That means signals, some signal will be lost. But in optical fibers, because all the signals are converted to, see, electrical signals are converted to optical signals, okay, optical signals. So electrical signals will be converted to optical signals and then transmitted through optical fiber. And what is the advantage here? Because see here, this transmission happens. See, if you have, you can just bend the optical fiber like anything, but there will be no problem in the transmission, okay. So suppose you have optical fiber like this. So what happens here? Total internal reflection happens, and multiple total internal reflection happens, and the signal. So total internal reflection means there is no loss, no transmission, nothing. So no loss of the signal. You'll get the whole signal out over here. So if you have intensity in, like in the beginning, intensity of the signal is I. At the end also you will have the same intensity of the signal. So this is the advantage of using optical fiber. Now we'll just go to the technical details or physics behind it. Physics behind it. So as we have told that, as we have learned that there are mainly in the optical fiber you have, so optical fibers are actually of shape of tube. But if you just cut a tube, if you cut a tube and see the cross sectional view, it will be kind of rectangle, okay. The thing we are seeing here is the cross sectional view. This is the cross sectional view, of the optical fiber, okay. A single tube. So optical fiber can be many such optical fibers as I had shown you. So in the telecommunication, single fiber can actually carry or carries conversation 2000 conversation almost. So many more informations you can transmit from one place to another. Okay, if you use optical fiber. Anyway, so in this case, you look, you have two two materials of different refractive indices. One is called cladding, which is lesser refractive index, and the core material, as I said, it may be may be made of, the core material can be made of silicon or quartz or very good quality glass. Okay, very good quality glass, this core, and it has refractive index greater than the cladding. Cladding is made of some glass which has refractive index at least lesser than, little bit of lesser than, like slightly lesser than the NO1. Okay, so this is core and cladding. Now you must be a little bit bored what you are saying, sir, core and cladding, like many times. Anyway, see, look here, what happens, signal does not pass from core to cladding, does not transmit. Okay, does not transmit. What happens, everything gets reflected. See, this is the outer portion, suppose in the, like, just entrance of the tube. Okay, entrance of the tube here, suppose a light signal is just entering into the core material, and when it goes here, look, I have at this is the interface, I have two medium, one is having refractive index N2, another one has refractive index N1, and see, N1 is greater than N2. That means the light is going from denser medium to rarer medium. So when light goes from denser, suppose this is rarer medium, okay, and this is denser medium. So when light goes from denser medium to rarer medium, what happens? Light rays generally goes away from the normal, that is fine, but when the angle of incidence is greater than certain critical angle, so this critical angle is actually differ di different, it will be different for different combination of material, suppose N1 and N2. Okay, so it depends on, so critical angle depends on the refractive indices of the material you have. Okay, here, so this material N1 and N2, the refractive indices are chosen in such a way that when the light enters into the optical fiber, angle of incidence will be such that it will be always greater than IC. That means greater than critical angle. When it is becoming greater than critical angle, then the total light will be reflected back to the core itself. It will not transmit through it, and it will not go to the cladding. Okay, it will not go to the cladding portion. So similarly here again, it will be, this angle of incidence will be greater than the IC, so it will be reflected back to here. Here also the same thing will happen always. So there will be an angle, or there will be a cone. Okay, cone like this, I'll just show you. Between them, okay, there is a limit. Obviously this angle of incidence, you have, like, at any angle of incidence you cannot have theta greater than IC inside the core. Obviously there is a limit, okay, there is a limit within which whatever light enters into the optical fiber will be suffering total internal reflection, because theta will be greater than IC. So that particular angle will be called as angle of acceptance. Okay, angle of acceptance, and that can be calculated. See here, so this is the cone. So I have shown you from this side, even this side, if you just if you have light from this side also, whatever light you see, it will come and it will be having or suffering total internal reflection. Okay, so within this cone, okay, within this cone, whatever light goes, they will suffer total internal reflection. Okay, all right, so this is called angle of, so this is called cone of acceptance. Okay, this is called cone of acceptance. All right, so this is called cone of acceptance. Okay, so whatever light you see, they will suffer total internal reflection within this cone. And there is a formula for this particular angle of acceptance. See, this angle, half of the angle of the cone is called angle of acceptance. If this is alpha, then we can just actually apply here sine alpha. It is air, outside air. Air means n1. N1 is 1. So sine alpha is the angle of incidence over here. So angle of refractive index will be here n1 into sine 90 degree. Okay, sine 90 degree, the critical, at the critical it will be here critical. This is actually, okay, so I'll just tell you what is happening here. What is the formula for this acceptance angle? The sine alpha will be actually given by under root n1 square minus n2 square. So this is called numerical aperture also. This is called numerical aperture. Okay, so this is called numerical aperture also. Okay, sine of that angle is called numerical aperture. Alpha is the angle of acceptance. This cone is called cone of acceptance for this particular optical fiber. So because it depends on refractive indices of the core and cladding material, so this angle of acceptance will be differing for different optical fibers. And the sign of that angle of acceptance is called numerical aperture. It is in short NA. It is called numerical aperture. Numerical aperture. So there will be questions in like competitive exams from this particular numerical aperture and what all concepts you have in this optical fiber, etc. Okay, I have seen there are questions in JEE Advanced as well as JEE Mains from this particular topic, optical fiber. So if you have any doubt, you can ask me now, or else I'll just go to the next topic. Next topic in the sense I'll take up few good examples, numerical examples today, depending on the concept of total internal reflections. Deepak, do you have any question here over here? Core cladding and how optical signals are transmitted and why is it being used instead of using some other fibers or other conductors. For even electrical signal in the telecommunication, electrical signal is sent via these optical fibers nowadays, and optical signal, and that the internet will transmitical will be converted to transmitted up to our receiver, and from that there is something called transducer, who actually again is a complex process. And yeah, so this is why modern life is becoming so luxurious nowadays because of this technological revolution. Okay, Deepak, in optical fiber. Okay, if not, then I'll just go to the next slide. Okay, there is a question over here. This is being asked in some year, I don't know exactly which year it is, in IIT JEE question paper. So the question is, a point source of light S is placed at the bottom of the vessel. Okay, at the bottom of the vessel containing a liquid of refractive index 5/3. A liquid, so this is a liquid which is placed inside the vessel, as you can see. So refractive index, if I write mu or n, you write anything. So this is 5/3. Okay. Now the question is, a person is viewing from the above of the source. So source is here, person is viewing from here. Okay, from here. Okay, person is viewing from here. There is an opaque disc of radius 1 centimeter floating on the surface. That means, see, you can see this part. This is an opaque. Opaque in the sense it allows the light. This is an opaque material in the sense not allow the light to pass through type of disc. Okay, kind of disc. This is opaque material. Okay, disc means it has some thickness as well. Kind of, like so this is a disc. So kind of this is opaque. Opaque in the sense it cannot pass light through it. So this is called opaque. So such a material is placed on the top of the surface, and that this material has actually radius 1 centimeter. This disc, opaque disc. There is an opaque disc of radius 1 centimeter floating on the surface. The center of the disc lies vertically above the source. The center, just in the same line, the source is actually. So this, suppose this is the center, in the same line, the source is situating, as you can see from this figure also. Okay. So if some person is viewing from this particular place, only from this place, okay, he definitely will not be able to see the source. Okay, so liquid, now what you have to do, if you drain the liquid of the vessel gradually using a tap, what is the maximum height of the liquid for which the source cannot be seen? That means, look here, you might be thinking why it is not been seen. First of all, you might be thinking, why is it so it will not be seen? Because of this opaque disc. Opaque disc. Even if this opaque disc is not there, sometime you may not be able to see. Why? I'll tell you why it cannot be seen. Look here. When you have a source at the bottom, sometime actually, the fishes over here, fishes in the lake and all, they see light, they cannot see light in between. Okay, so they see. Okay, anyway, so we'll discuss this. I think this is there in NCERT textbook. You can just read, like, go through this. Oh, sorry. See, they can see only this portion. Okay, beyond that they cannot see. So they can see things through this particular circle. They cannot see beyond it. I'll tell you why it is so. Okay. Beyond this circle, or I can say beyond, see this is a cone, kind of a cone. See beyond this cone, whatever light comes from outside world, they can see through this cone. Outside this cone, whatever light comes, they cannot see. Okay, I'll tell you why. Okay, let us see from here first. See, if a light comes from here, see, I'll just take two representative light signal, light rays. So one is coming here, S through this, like in this line, SB. One is SB, and another one is SA. These are two rays I'm just taking for our discussion. And see why you cannot see, sorry, yeah, why you cannot see beyond this particular, this, you know, because see, suppose the light which is suffering refraction, see this is the air and this is the water, this is the water, or maybe some other material like other liquid, in this case 5/3, some other liquid. So there is an interface, so light will be actually getting refracted. Now if this is air, so light is going from, see this is denser medium and this is rarer medium. Whenever it is going from denser to rarer, so there is a chance to have total internal reflection. And for what is the condition for total internal reflection? That is, you have to have sin theta c, okay, or so when it is sin theta c, then it will be, so suppose I'll write n1 sin theta c is equal to n2 sin 90 degree. This gone. So it will be, see n1 means refractive index of this material, and this is air in this case, n2 is air. So sin theta c is equal to 1 by n1 if I say air is 1. Okay. So if the angle of incidence over here is somehow at the critical angle, then the light will be grazing the surface interface. Grazing the interface, that means, see, light will be at critical angle of incidence. Generally light will be, see, sin r, as I said, sin r will be 90 degrees, so this will be refracted, angle of refraction will be 90 degree, so it will be grazing the interface itself, grazing the interface at the angle of incidence. So if somehow the light rays which are coming from the source at the interface, if the angle of incidence is exactly equal to theta c, then the light ray will be grazing. That means you will see the light rays will be passing through this. It will no longer go to your eyes. Okay, it will no longer go to your eyes. They will just be on the surface of the water itself or interface itself. So whatever you see, you must be able to see in this range. Okay, that's why I said in the lake, fishes can see things in between this radius or in between this thickness. Okay, they cannot see things beyond this range. Okay, beyond here they cannot see here things over here. They can see whatever, like whatever things are here. Okay, they can see from here, like in between this cone. Because if see I take another ray which has, see this is my angle of incidence. Now see, angle of incidence is greater than this angle, then the light will go to medium like this. Okay, here also, if it is beyond the critical angle, then we'll come back to the liquid itself. It will not go beyond that. So using this formula, we have to find out the height. Look, if I say this is sin theta c, this is theta c, at this particular situation, the light is grazing. So I can write the formula. So sin theta c is equal to 1 by mu that we have already shown you. And in this case, you have to use the geometry, as it is geometrical optics. You have to use the geometry. Okay. So using that geometry, we have to find out a relation between mu, r, h, etc. Let us see. We will try to find out the relation between all those parameters, and then thereby we will find out the height till which it cannot see. Okay. Because yeah, so if the disk is there, see, look, the disk is here. That means if this is the height h, so the if the water level is up to here, it cannot see, it cannot be seen. If the water level is somewhere here, look here, somewhere here, it comes down, then look, this refract, see, the angle of incidence theta c will be satisfying some greater angle, isn't it? Some greater angle. Then you might see your cone will be like this. Okay, so you will be able to see up to this radius. Okay, the question you have to look here, there is an opaque disc of radius 1 centimeter floating on the surface. The center of the disc is exactly vertically down to, like, above to this source. Now the liquid is actually being drained so that you can see the light source, but at this particular situation you will not be able to see, because of total, see, critical angle at this particular situation. Suppose it is and critical angle situation, that's why this, your source will be exactly below the disk. You will not be able to see if the water, see, if the water level is up to here, at this situation you will not be able to see, okay, or light coming out from the source, you cannot be able to see. So this is the condition for critical condition of critical incidence, critical angle of incidence. So if this kind of question comes, you have to use this condition of angle of, like, critical angle of incidence. So you have to write simply sin theta c is equal, so this angle of, so this angle of incidence, this angle is theta c. So this, by geometry you will get, because these are opposite angle, so you will get this also theta c, this also theta c, if this is theta c. Okay, so these are theta c, opposite angle. Okay, if this is bit hazy, then I'll, why I am giving so much stress to this question, because this kind of questions only will come from this chapter, particularly this portion, total internal reflection, this part in the competition. So if this is theta c, so this also will be theta c, the half of the, I can just write as will be theta c. Now from this, the sin theta c, we know from our condition of critical angle of incidence. Now we'll use this sin. What is sin theta c? From geometry, it will be perpendicular r by your hypotenuse is this one, SA. Okay, if I just take the triangle, if I just take the triangle SOA, this triangle I'm taking, this is a right angle triangle, this is 90 degree, this is theta c from here. Okay, opposite angle. So this is your hypotenuse for this particular triangle, so it will be given by r square plus h square. So you got this as sine theta c, but you have already from here sine theta c is equal to 1 by mu. So you can just equate to 1 by mu. So you know the value of 1 by mu. So what I'll do, I'll just do the calculation in the next slide maybe. So I have got sine theta c is equal to 1 by mu, that is equal to perpendicular by hypotenuse, that is r square plus h square. Okay, so what are the informations given over here? Before I go to that informations, let us do a little bit of simplification. This you can write 1 by mu square, then r square divided by r square plus h square. Okay, height, and see, we can do one thing, r square plus h square mu square. So h square will be is equal to r square mu square minus r square. So if you take r square common and take root over of that, will give you, so mu square minus 1. So this will give you the height, that particular height. Okay, so now we'll just find out what are the informations given over here. See, informations are given. The refractive index 5 by 3 is given, so mu is given, and radius of this circle r is given. Okay, disk, radius of the disk is given r. So if r is given, then everything is done. So r is given as 1 centimeter, so which can be written as 10 to the power minus 2 meter, and mu is given 5 by 3. Okay, now you just put it here. Okay, if you put this, okay, so h will be, r means 10 to the power minus 2 into, so this is 25 by 9 minus 1, so this will give you 10 to the power minus 2. Okay, let us see how it goes. So this will be 16 by 9, so it will be actually 4 by 3. 4 by 3. Okay, so okay, let us keep it in centimeter. It is actually in meter now. So actually this, I'll just keep it in centimeter, so it will be almost 1.33 centimeter. Okay, so 1.33 centimeter. So this is the height. Till that height, the person cannot see the source of light or any light from the source. But if you drain the water, what will happen? If you drain the water gradually, so suppose the level is somewhere here, water level, then your cone will be greater than the disk itself. Okay, look, this is the radius of the cone. So in that case, you will see some lights from here, through here. Okay, some lights you will see through this. Okay, so this is what the question was. Now I'll take up 2-3 more questions from here. One, okay, so I'll just write the question. You have to just see. Suppose there is a triangle. I mean to say there is equilateral glass prism. Suppose there is there is an equilateral glass prism, and it has refractive index 3/2, that means 1.5. Okay, 1.5. Now this can be named as A, B, C. Suppose this is A, B, C, and a ray of light is actually coming an incident. So this is actually in getting incident, normal incidence. Okay, suppose this is normally incident. Okay, normal incidence. Light falling normally to AB surface. Okay, AB surface, refracting surface. And suppose this whole prism is kept inside the water. So this is glass and this is water, whose refractive index is 4/3. So the question is, will this ray suffer the total internal reflection on striking the AC? So AC is another surface. Suppose this is getting refracted. After refraction, it will just go and strike over here. So the question is, after striking this, whether whether this ray which is taking the AC, which is falling normally on this AB prism, would totally of the suffer internal reflection. You have to justify your answer. This is a kind of question which is asked in uh, cbse board exam. So I hope you have understood the question. I'll just write little bit. So ray of light actually normally falling normally. Okay, it is normal incidence. Okay, at AB. So the prism, it is actually prism, equilateral prism, equilateral prism. So there is an equilateral prism which is given here in the figure ABC. So on the AB surface, refracting surface, a light ray comes and falls normally, and then after refraction from here, it will just go and hit over here. After hitting here, whether the light will undergo total internal reflection. So this is the question. So how to solve this? First of all, you have to know that equilateral triangle is also 60 degree, this is 60 degree, this is also 60. Okay, and when this ray is actually normal to AB, there will be no refraction. It will actually passes through. It will passes through. For the case of normal incidence, it will pass through. Okay, I think I'll just take the ray somewhat little bit above normal incidence. Okay, so when it is normally getting incident over here, so it will actually pass through and hit over here directly. It will not bend. Okay, directly come here and hit, because in case of normal incidence, there will be no refraction. It will just transmit or passes through like this. Okay, it will passes through. Now if you just draw a normal over here, it is normal to this surface AC. This, suppose this is the normal. So this is your angle of incidence. Okay, angle of incidence. What is the angle of incidence? You have to understand. So since this is 60 degree and this is angle of incidence, normal incidence. Okay, normal incidence. Do you have any answer? So what will be this angle of incidence for this? What is this angle of incidence? What is the value of this angle? The answer is here. The angle of incidence will be 60 degree. Okay. So if the angle of incidence is 60 degree and this is a glass and obviously within water, so you have to find out what is the refractive index of this glass with respect to water first. Okay, glass prism with respect to water, that means refractive index, if you write mu g glass with respect to water like this, then you have to write mu g over mu w. This value you have to first write. So mu g is 2 over 3 and this will be 3 over 4. So it will be 9 by 8. This will be refractive index, okay, of the prism. Now you come here. See, you have to find out the total internal reflection will happen only when your angle of incidence is greater than IC. So always whenever you are asked to find out whether there will be do first is to find total internal reflection. What you have to do is find out what is the critical angle case. So in this case, interface is water and the glass. Okay, water and glass. So you have the refractive index of the glass prism with respect to water you have got already. So in such kind of interfaces, how much will be the critical angle of incidence? So you know the formula. Sin IC will be equal to 1 by refractive index, right? 1 over refractive index. Here mu g over water. Okay. So this you have already got. You can write. So it will be 8 by 9. Sin IC is equal to 8 by 9. And if you want to find out IC, then it will be sine inverse of 8 by 9. Okay. So 8 by 9 means this is actually less than 1. It will be something like, see this value 8 by 9 will be somewhat 0.89, something like that. That means it is below 1. So below 1, see sine 60 degree means what? Root 3 by 2. Okay. And sine 30 degree means half. That means 0.5. This is 1 point. So it will be 0.8, kind of 0.8. Okay. And this will be 0.5 sine 30 degree, 0.5. So if you have here 0.8, okay, and sine, okay, and 90 degree, sine 60 degree, 60 degree will be 1.3, sorry, 1.2 means 1.2. So it will come around 0.8686. So this this is the critical. So this 60 degree is becoming less than critical angle. I don't know whether you are understanding. Deepa, can you just respond to me? I'm just thinking like it is becoming abstract to you. Is it okay? Are you understanding? Are you able to hear me? What I'm doing over here? What was the question? Do you understand what I'm trying to do? Deepa, are you able to hear me? The question was, we have to find out whether there will be total internal reflection upon hitting the surface AC or not. So we have to find out, in these cases, we have to find out what is the critical angle for the system given. Okay. If the critical angle is less than the angle of incidence, in this case 60, then there would have been total internal reflection happening. But if it is less, then total internal reflection will not happen. So in this case, what we have got, look, I'll just quickly write over here. You have to be little bit strong in calculation in this kind of cases. So the interface, you have to find out what is the interface, and for that interface what will be the critical angle. So in this case the interface was glass, and between glass and water. So you have to find out what is the refractive index of this prism with respect to water. So that's why we have found out this mu g by mu w. Okay, so it was found to be this. Now we know formula for critical angle, sin theta IC is equal to 1 by mu GW. So this will be, this side will be 8 by 9. Okay, so this will give you something like 0.89 or something. Okay, 0.89. But sin theta, so sin theta IC is actually 0.89. But here in this case, sin theta I is 60 degree over here. This is actually root 3 by 2. Root 3 means 1.732 divided by 2. So you will get 0.866, etc. Okay, so this value, look, this value is less than the value of this. That means your angle of incidence is less than, in this case angle of incidence is less than the critical angle. So there will be no TIR, total internal reflection. Okay, so this was the question. So this kind of question will be asked. There are actually very like many examples on this. So what I'll do, I'll just give some standard examples or standard questions which are being asked in various competitive exams in the quiz sheets that will be available in our site. You can just see from there. So I think I'll be stopping it here. So what we have discussed, I'll just summarize. Today we have discussed optical fiber. Optical fiber, I have just told you the concept and what are the applications, possible applications. Like, see, in the medical also we use this optical fiber. Okay, optical fiber, in fact optical, like tube, optical tube we use. You might be surprising. See, optical fibers, any surgical like any surgery, basically internal surgery is being done with this optical fiber. Okay, and mainly this endoscopy, etc., is being done with this optical fiber, with the help of optical fiber. Okay, so here the important formula what you have to remember is this one, the numerical aperture. Generally there will be question from numerical aperture and many other things. Obviously I'll give you some questions in the quiz sheets depending on this optical fiber, total internal reflection, and etc. So up to whatever we have learned, we'll give a quiz question immediately on this particular portion. So we'll start directly with the lenses, spherical lenses, and refraction through spherical lens, and how image formation happens in spherical lenses, etc. Okay, so I'll stop it here today. If you have any questions so far, you can ask me, Deepa.
Working.
Do you understand everything?
Yes, sir.
Okay. All right. I'll send some quiz questions, so you will be able to get it from our website. You can see whether you can solve those questions depending on this kind of concepts, whatever we have learned. Okay. So
Working,
bye
sir.
for today.
Thank you, sir.
Welcome.